When we look up from Earth on a clear night, the cosmos appears perfectly still. The stars seem fixed in a vast, silent ocean, giving us a deep sense of tranquility and permanence. That stillness is a complete illusion. Right now, the Earth, our solar system, and the entire Milky Way galaxy are hurtling through space at over 2 million kilometers per hour. This animated model of an inflating balloon illustrates the baseline expectation in astrophysics. Because the universe is expanding, galaxies should drift away from one another uniformly, exactly like these dots spreading out on the stretching rubber surface. But in the 1970s, astronomers measuring the movement of nearby galaxies found a serious anomaly. Instead of drifting apart at predictable rates, thousands of galaxies were moving unexpectedly fast toward one single localized region of the sky. Astronomers call this extra localized movement peculiar velocity. Its presence confirmed that an immense, unseen source of gravity was actively hijacking the trajectory of our entire cosmic neighborhood. If an entire sector of the universe is being forcefully pulled toward a specific destination, the obvious response is to simply look ahead and see what is pulling us. Except we can't. Our line of sight is entirely blocked by an obstacle astronomers call the zone of avoidance. Looking at this photograph of the Milky Way, you can clearly see thick, dark dust lanes running straight through the bright stellar core. We are trying to look outward through the dense, flat disk of our own galaxy, and those billions of stars, massive clouds of gas, and cosmic dust act like a solid wall against visible light. This internal galactic debris completely absorbs optical light. It creates a massive blind spot sitting exactly where our astronomical instruments need to look, rendering standard telescopes entirely useless. Our galaxy is locked into a high-speed, inescapable voyage, but we are flying blind, unable to see the massive structure waiting directly in our path. To pierce the zone of avoidance, scientists had to bypass optical light entirely. This image shows the kind of radio telescopes that, along with X-ray satellites, detect high-energy frequencies that easily pass right through the galactic dust. By mapping these invisible signals, astronomers finally unmasked the destination sitting 150 to 250 million light-years away. They named it the Great Attractor. The name sounds terrifying, and early theories suggested it might be an unimaginably massive black hole slowly swallowing nearby space. Modern observations prove that wrong. A black hole large enough to exert that much force would emit distinct gravitational signatures, which simply aren't there. Instead, the Great Attractor is an immense region of space anchored by the Norma Cluster, containing thousands of galaxies, galaxy clusters, and vast amounts of intensely hot gas. But visible matter alone cannot explain the force we observe. This 3D topographical gravity map illustrates the solution. To generate enough pull to influence 100,000 galaxies, the physical cluster in the center must be surrounded by a massive halo of invisible dark matter. Dark matter neither emits nor reflects light, but its gravitational grip on the galaxies around it is undeniable. The Great Attractor is not a single solid object, but rather one of the largest, heaviest concentrations of dark matter and galactic clusters we have ever mapped in the local universe. And the Milky Way isn't making this journey alone. This photograph shows the Andromeda Galaxy, our massive neighbor. Andromeda, along with our entire local group of galaxies, is caught in that exact same gravitational current. Mapping further out, astronomers found something larger. This coordinate map shows the Great Attractor here, but beyond it is the Shapley Supercluster. Its immense gravity dominates the region, actively pulling the Great Attractor and everything in its wake toward it. We are seeing the macro architecture of the universe at work. Across millions of light-years, galaxies arrange themselves in a vast cosmic web. They form dense structural filaments separated by gigantic empty voids. The terrifying speed of our galaxy is just the natural result of gravity. Slowly, over billions of years, it drags us along these cosmic filaments toward the heaviest, densest regions of space. Knowing that we are hurtling forward at 600 kilometers per second, the math demands an answer. When do we finally arrive? And what happens to our solar system when we crash into this gravitational giant? The answer is that Earth is perfectly safe. The Great Attractor's gravitational influence only dictates motion across enormous intergalactic distances. It has absolutely zero measurable effect on our sun or the planetary orbits within our solar system, and the physics of the universe guarantees we will never crash because of an opposing force, dark energy. While gravity pulls us through space, dark energy is continually stretching the fabric of space itself. Think of it like this visual metaphor of a cosmic treadmill. Gravity acts like the forward motion of the sphere, trying to cross the distance. But cosmic expansion is the surface rapidly stretching backward, constantly creating new, empty space between us and our destination. Over immense timescales, the stretching of the universe outpaces our forward velocity. Because space is expanding faster than our peculiar velocity can cross it, the Milky Way will never actually reach the Great Attractor. We are a single traveler on an infinite voyage, locked into a high-speed pursuit of a massive, invisible horizon, one that the universe will never allow us to catch. You probably feel like you're sitting perfectly still right now, but that feeling is an illusion. As you watch this, the Earth is spinning on its axis at 1,000 miles per hour, while simultaneously orbiting the Sun at 67,000 miles per hour. Beyond our solar system, the entire Milky Way is rotating, carrying this around the galactic center at 500,000 miles per hour. Since the Big Bang, space has been stretching, pushing galaxies away in a uniform, predictable extension. But in the 1970s, astronomers found our Milky Way isn't following that grid. We're being pulled sharply off course at 600 kilometers per second toward a single coordinate. Standard expansion cannot explain this movement. The data points to a gravitational force large enough to drag our entire galactic neighborhood across the cosmos. Astronomers trace this trajectory to a region of space located past the constellations of Norma and the Southern Triangle. However, peering into that region is nearly impossible. It sits within the zone of avoidance, a part of the sky hidden by the thickest section of our own galaxy. Looking toward this anomaly requires looking through a dense collection of gas and cosmic debris. This creates an opaque wall blocking traditional optical telescopes. We are plummeting toward a massive gravitational anomaly that remains hidden from sight. Astronomers call it the Great Attractor. To see what lies behind the dust, scientists had to look beyond the spectrum of visible light. They used radio waves, specifically the 21-centimeter emission from neutral hydrogen. These long wavelengths travel through galactic debris without being scattered or absorbed. Capturing these signals required sensitive radio telescopes, such as the 64-meter Parkes dish in Australia. These instruments allowed astronomers to conduct surveys that revealed thousands of previously hidden galaxies. These radio maps finally converted the Great Attractor from a mathematical anomaly into a physically observable region of space. The data shows the Great Attractor is a vast region of space, dense with both visible and dark matter, rather than a single massive object like a black hole. At the center of this region lies the Norma Cluster, one of the most massive and densely populated galaxy clusters in our local universe. Nearby structures add to the pole, including the South Pole Wall, a colossal filament of galaxies and gas stretching 700 million light-years across. These structures form a larger supercluster called Laniakea. This 3D map shows the interconnected web of matter defining our place in the cosmos. The Great Attractor is the gravitational center of this supercluster, functioning as the lowest point in a massive cosmic basin. Our galaxy acts like a small boat caught in a current, naturally flowing along these gravitational lines toward the center of the Laniakea structure. Since we are falling toward this center at 600 kilometers per second, it seems inevitable that the Milky Way will eventually reach it. However, we will never actually arrive. Our galaxy is caught in a tug-of-war. Gravity pulls matter inward, but dark energy stretches the fabric of space-time, pushing everything apart. Laniakea is too sprawling to stay together forever. The expansion of the universe is winning the fight. The space between the Milky Way and the Great Attractor is expanding faster than we can travel through it. On a macro scale, the force of expansion is overcoming the pull of gravity, ensuring that these massive structures will eventually pull apart. In the distant future, the Milky Way's trajectory toward the Great Attractor will slow down and eventually reverse. As the expansion of the universe accelerates, the immense gravitational ties holding the Laniakea Supercluster together will snap. Galaxy clusters will begin to move away from one another, drifting like islands in an ever-widening cosmic ocean. The Great Attractor is a temporary anchor in an accelerating universe, a snapshot of a cosmos that is constantly in motion and slowly pulling apart.
The universe is full of mysteries waiting to be discovered. Join Science Unlocked TV